Hello and thank you for tuning in to my YouTube channel Lapping Analytics. As the title indicates, today's video is about research and more specifically about what to do with small sample data. If you are a researcher or in some way responsible for a training program offered by your organization and you are struggling to get most out of a small sample of data that you've gathered, but you've basically been told that your data is rubbish and that there is nothing you can do, this video is for you. Because in this video I am going to talk about two possible solutions for your data, whether you are dealing with quantitative data, qualitative data, or a mix of both. The first solution is one that I already dedicated a video on about 9 months ago, just before Christmas, and is based on the percentage of overlap, or technically speaking non-overlap, of particular parts of data. And the second solution is one that I have not yet called it by its name in my videos thus far, but have been using as part of a predictive model for match outcomes in football or soccer. This second solution is also known as Brunner-Monsel's test, and here you find a screenshot of an open access article that presents this procedure very elegantly without a lot of high-level mathematics. What both solutions have in common is that they can be run in freely available open source programs such as R and Jamovi, and I use them on a regular basis. So what I'm going to do in this video is briefly explain and compare both solutions with a small sample data example. Suppose that your research or training team is interested in whether a sales training program can help to boost the quality of arguments in conversations, the aim of which is to sell a particular product. We have 16 candidates who are interested in our program, but there is only space for 8 in each of 2 editions. So we randomly allocate the 16 candidates to the 2 editions and have a conversation with each of the 16 candidates after the first edition. As a result, the 8 candidates who still need to take the program and will do so in the second edition form the control group. Each conversation on a specific topic for a specific product is rated on an ordinal scale from 1 to 4, with 1 indicating a poor performance, 2 a borderline performance, 3 a satisfactory performance, and 4 an excellent performance. So in the control group we get 3 poor performances, 3 borderline performances, 1 satisfactory performance and 1 excellent performance, whereas in the group of 8 candidates who just completed the training program, we find no poor performances, only 1 borderline performance, 3 satisfactory performances, and 4 excellent performances. In a bar chart, these results look like this. Now, the first solution, which I also proposed in a video 9 months ago, albeit in a different type of context, is about the percentage of all non-overlapping data, hence abbreviated PAND or PAND. The key question here is, what is the minimum number of data points that we would need to eliminate in order to get perfect non-overlap? The answer is 3. The borderline performance in the training group and the satisfactory and excellent performances in the control group. So this yields a percentage of all non-overlapping data, or PAND, of 13 out of 16, so that would be about 81.3%. I use a slight modification of this statistic in my own research, which includes a so-called prior distribution to avoid extreme estimates based on very small samples, and helps to acquire a so-called credible interval that can be used for testing purposes. Now, without going into more mathematical detail of that, which you can find anyway in my other video, the conclusion here would be that the training group clearly outperformed the control group. Next, the second solution works a bit differently, but we will see in a bit that it yields similar results. For this second solution, we can represent the data in the form of a matrix, in which each rating of each group is compared with each rating of the other group. Given a sample size of 8 in each group, this comes down to an 8 by 8 matrix, hence 64 comparisons. The comparisons in blue are positive numbers and indicate that for the comparison at hand, the training performance was better than the control performance. The comparisons in red indicate the opposite, that is, a better performance in the control group. And the numbers in gray are zeros and indicate an equal performance. So there are only 5 comparisons in favor of the control group, 10 indicate a draw or tie, and the other 49 comparisons are in favor of the training group. Now, let's convert these frequencies into probabilities. As I said, there are 5 comparisons in favor of the control group, here in red. 10 indicate a draw or tie, here in gray, and the other 49 are in favor of the training group, here in blue. Given a total of 64 comparisons, these frequencies correspond with percentages of 7.8%, 15.6%, and 76.6% respectively. To use a sports example for a moment, if this model were to be used for the prediction of a football or soccer match, this model indicates a 7.8% chance of the control group winning, a 76.6% chance of the training group winning, and a 15.6% chance of a draw. And if this was a match in the playoffs of a tournament, meaning that ultimately a draw is not a possible outcome because there has to be a winner, the draw probability would be split into 2 equal halves, and that would then result in a 15.6% of the control group winning and an 84.4% chance of the training group winning. And the latter are the point estimates that one can get in programs like R and Jamovi with Brunner-Munzel's test, along with a confidence interval if that is of interest for testing and or interval estimation purposes. In a bar chart, the outcomes of the 64 comparisons look like this, with again 7.8% of the bar surface in red, 15.6% of the surface in gray, and the clear majority of 76.6% of the surface in blue. And after splitting the gray area into 2 equal halves, 15.6% in favor of the control group and 84.4% in favor of the training group. Note that the 84.4% is a bit higher than the 81.3% we get via band, the first solution that I presented, and this is because in the second solution, the Brunner-Munzel test, all ordinal information in the 1, 2, 3, 4 rating system is used, whereas band only looks at overlap versus non-overlap and therefore does not use all of the ordinal information. If instead of multi-category ordinal ratings we use dichotomous ratings, for instance pass-fail ratings, both solutions would for this dataset yield the same point estimate as percentage in favor of the training group. So what does this all mean? Well, we have seen 2 solutions, Brunner-Munzel's or abbreviated BM test, and band, the percentage of all non-overlapping data, where the B between parentheses is the variant, the Bayesian variant that I normally use, which includes a prior distribution, as I briefly explained earlier, and you can find in the other video that I shot 9 months ago. While the example used in this video is purposefully an ordinal data example where 1, 2, 3 and 4 constitute clear ordered categories, but not everyone may agree that the difference between 1 and 2 in actual performance is the same as the difference between 2 and 3 or between 3 and 4, the BM test can be used for quantitative, ordinal and dichotomous data, with the note that for dichotomous data there will be a clear interest in one particular outcome, for example pass. However, one drawback of the BM test is that that can actually be circumvented by the other solution, PAND, is that the BM test requires a clear natural order of numbers or categories and therefore cannot be used for so-called multi-category nominal data. For example, if instead of rating the quality of arguments, we coded which of 3 or 4 possible approaches a candidate takes in a conversation, and there is no clear order of approaches in terms of one necessarily being better than the other, these different approaches constitute a 3 or 4 category nominal variable for which the BM test cannot be used. For this kind of situations, however, PAND and its Bayesian variant PAND-B can be used. Basically, this all non-overlapping data solution can be used for any kind of data, with the nuance that for multi-category nominal data, its exact calculation will depend on whether we are interested in general non-overlap or in specific local non-overlap. For more details on this matter, again, I refer to my previous video, the one that I mentioned at the start of this video. And well, it has had quite a few views already, so you will find if you you sort on popular videos, it will probably pop up still in the top 3 or top 5 of videos that I did so far. And there are also a few things that the two solutions presented in this video have in common. One of the commonalities that I already mentioned is that for quantitative, ordinal and dichotomous data, both solutions can be used. In addition, when dealing with dichotomous data in equally large samples, both solutions will yield the same point estimates. So if, for instance, PAND yields 80% of non-overlap in the direction of the training group, the BM test will also yield a point estimate of 80% in favor of the training group. However, in line with what I mentioned earlier, when dealing with non-dichotomous quantitative or ordinal data, the BM test can use all order information, whereas the other solution is limited to overlap versus non-overlap and may therefore give slightly less accurate estimates than the BM test. Meanwhile, another feature that both solutions have in common is that they work best when the sample sizes are equal or at least almost equal. That is, when sample sizes are clearly different, both methods can sometimes give somewhat strange, implausible outcomes. And the BM test works best if both samples have at least 7 observations, whereas PAND, and in my view especially PAND-B, can be used for even smaller samples as well. So to sum up, PAND and its Bayesian variant can be used for all data types and therefore probably will be more useful when dealing with qualitative data compared to the BM test. And the latter, the BM test, tends to be somewhat more accurate when dealing with quantitative data or ordinal data, which may be conceptualized as either quantitative or qualitative, by the way. So in any case, at least if you deal with a mix of qualitative and quantitative data, a combined use of these solutions may be most appropriate. And that's it for this video, which I hope you find useful. Feel free to leave a comment below the video or use the email address listed in the description of this video to get in touch. And for now, thank you for watching, thank you for listening, have a great day, and see you soon.